Who here tracks their home's energy use? Okay, I'll pick you. How are you doing? What sort of metric do you use?
I pay the electric bill for me and my roommates, so I get mad at them when it's high, and I turn off the lights and tell them not to use the dryer as much, etc. But just the electric bill basically is what.
So it's sort of an intuitive tracking. If it's painful to make the payment, then okay. So that's one way to track it. Does anybody do something a little more analytical than that? Like yes.
I have an energy monitor that monitors electricity throughout the day and also look at my gas bill.
So do you know how many BTUs or kilowatt hours your house uses,
Yep.
dwelling unit uses in a year?
Mhm.
And how's it doing?
Pretty good. We do about 390 kilowatt hours a month.
A month for total energy or just electricity?
Just for the electricity.
All right, and is it gas for
I
heat?
can't remember how many therms of gas. But
All right. So you don't do a total energy metric.
Not right now.
Does anybody do a total energy metric for the? You do.
Yeah, I just receive a monthly report from my utility, and because I'm all electric, it's
All right.
what the profile would be. I'm guessing.
So your utility company's tracking it. You're not.
Sorry, but I
They have a vested interest in tracking it. All right. So the general sense I'm getting is that there's not a lot of rigorous analytical tracking of our own energy usage in our homes. Is that fair to say? Would someone like to argue with that? Loey?
I'll just say I rigorously did it and translated everything into BTUs for about 5 years, and then it was like, geez, I can do better. I can do other things with my time.
Yeah. Yeah. It's a testament to your resolve that it took you 5 years. So I'm going to be doing some numbers here because I think the Achilles heel of the environmental movement is our energy innumeracy. We're not keeping score, and if you don't keep score, you don't know if you're winning. It wouldn't be that much fun to go to a Red Sox game if there was no scorekeeping. So my second question was to anyone who was tracking was, have you done a major retrofit of your house? And if so, what was the impact on energy usage? But you've done a major retrofit. Did you quantify the impact on the energy usage?
Well, I rely on Eversource, which
Okay.
tells me how I compare to my average neighbors, and now I'm spectacular on the gas front.
Okay.
And horrible on the electricity front. 'Cause
Based on the smiley faces or the frowny faces? Okay. That's all right. I meant that.
That's true.
So gas is sold to you in therms. It's about $1.50 or so a therm. Electricity is typically sold to you in kilowatt hours. It's around 22.5 cents average per kilowatt hour. You can actually convert both therms and kilowatt hours into a common energy unit. I mean, you could convert the therms into kilowatt hours. You could convert the kilowatt hours into therms. What I do is convert them both into BTUs, just to be confusing. BTU is a British thermal unit. It's, what is it? The amount of energy required to raise 1 pound of water, 1 degree Fahrenheit, or roughly the equivalent of a wooden kitchen match burning down to the point where your finger starts feeling it. So what I have done is taken 3 sources of household energy, electricity, gas, and oil, and converted them to a common unit, BTUs, million BTUs in fact, so figured out how many kilowatt hours in a million BTUs, and then figured out how much you pay for that million BTUs. So I'm converting all 3 of those types of energy into one common unit, and that common unit is dollars and cents, because everybody in this room understands dollars and cents. So, a million BTUs of natural gas, that's the abbreviation for that is MMBTU of natural gas, costs, where does it do something? It's about, yeah, it's a little more than $15. Oh, there it is, $15.40. I'm using average prices. A gallon of oil, fuel oil, costs $22.35, and a kilowatt hour of electricity costs $65.92.
So that's a million BTUs.
That's a million BTUs, yeah, per million BTUs. So we're asking people to electrify their homes. So how does that make sense if a kilowatt, if a million BTUs delivered by electricity costs 4 or 5 times as much as a million BTUs delivered by natural gas? This is something to be aware of. So the second thing you have to factor in is how efficiently can you use those units of that type of energy. So how efficiently can you use natural gas typically? Does anybody know what an average efficiency for a boiler is? Maybe
90%, maybe.
90% for a good one that's humming along. So we'll use you know, a good oil boiler that's humming along is about. We'll use it. I'm going to compare 80% usage, 80% efficiency for gas and oil. So I'm going to convert. I'm going to do another conversion. You'll have to take this on. You can come up to me afterwards and get the detailed math if you'd like. But I'm trying to make a broader point here, so I don't want to get too much into the math because I will lose the rest of the audience. So if I'm burning that gas at 80% efficiency, then I'm getting that million BTUs is costing me $19.25 basically, because I'm not getting a one-to-one. The oil at 80% efficiency is costing me $27.94. So how efficiently do you think we can burn electricity, use electricity to I'm talking about space conditioning now. Any guesses?
100%.
100%. Would you believe it if I told you we can actually develop a system where you put 1 kilowatt hour of electricity in and you get 3 kilowatt hours of usable heat out?
Yes.
Would you buy that, Rich? That's what a heat pump does, a cold climate heat pump. Because it's not creating heat, it's moving heat. So it could be minus 17 outdoors, and that seems really cold, and it feels really cold, but there's actually a lot of heat in there, because the scale we're looking at is the Kelvin scale, or the Fahrenheit, the big scale where you go down to absolute zero. So that minus 17 Fahrenheit on the Kelvin scale is going to be lots of degrees. 300 degrees, something like that.
So you have 459
Oh, 400 something,
degrees
yeah.
less whatever.
Yeah.
Yeah.
I'm sure glad Mike's here. Yes.
This is a better.
Oh, all right. Thank you. So don't think in terms of degrees Fahrenheit when you're trying to imagine the amount of heat in the air. So that heat pump, there's a lot of heat that heat pump can grab in outdoor winter air, and through very efficient compression cycle, deliver usable heat into your house incredibly efficiently. And we have seen, if it's really well installed and really well engineered, over the course of a season, you can get about 300% efficiency. It's more typical to get maybe 280. It's possible to get 100 in a bad system, because electric resistance heat is 100% efficient because it's just 1-to-1. We don't want to use electric resistance heat. So if I assume, I'm going to be somewhat cautious here and say 280% efficiency, so that million BTUs of usable heat ends up costing me $23.54.
Wow.
So it's starting to even out here. And you can see why people are advocating converting from oil to electricity. If I'm at 300%, then that goes down to $21.97. And if my existing oil equipment is, or even if my existing gas equipment is kind of old, say at 75%, we're at 2053, so we're almost at parity there. So this is why people talk about cold climate heat pumps as an important strategy for getting us off fossil fuels, because it can work. Right now there still is an operating cost premium, and we can't forget that, particularly when we're talking about lower income communities. All right, so that's the miracle of energy units and fuel sources. So, do we care about, we care about dollars, we care about therms, we care about kilowatt hours, but what do we really care about? Carbon. That's correct. So, we're going to look at what this means for carbon quickly. Is this working? All right.
Yeah, we're fine. Keep going.
All right. Are you following, Mike?
I think so.
All right, good. All right, so we're gonna, just so that I can give you numbers that are greater than 0, but less than 10, I'm gonna take that million BTUs and turn it into 100 million BTUs. Just to move the decimal over to a point where it's a little easier to follow. And I'm going to convert that electricity and that gas and that oil to carbon. And that's based on current grid mix, ISO New England grid mix for electricity, natural gas at the best consensus guess about what the greenhouse gas equivalent for natural gas is, as you all no doubt aware. That's a controversial number. Could be much higher than anybody really wants to admit when you factor in the leaks. So, 100 million BTUs of New England, ISO New England is the electricity, is the New England grid. Independent system operator? Yeah. There's a cool app. I'll show it to you later if we have time. I have it on my phone that tells you in real time how much, where our electricity is coming from in ISO New England, what the sources are, what the cost spot market is. It's very cool. Anyway, take my word for it. So tons per 100 million BTUs. 8.51 for electricity. Gas is 5.30. Oil is 7.38. So it doesn't look so good for electricity, does it? That's because most of our electricity is generated by burning things, burning gas, mostly 60% gas, burning gas to heat up water, turning that water into steam and using that steam to run turbines that spin and then generate electricity. So the absolute best gas turbines, the best ones, and there aren't many of them, operate at about 60% efficiency. Yeah, that's not so great. Unless you're able to take that waste heat and use it for space heating. So you've got a combined heat and power plant. And a lot of, there are a fair number of places that do that, but generally speaking, that means you need to find a group of people who are willing to live near a power plant. And that's not always easy to do in this country. But so in the US, most of that waste heat is waste heat. And most of our plants are not anywhere near 60% efficient. So the grid mix is, let's say the grid is around 30–40% efficient, meaning a unit of energy in at the source, or 3.4 units of energy in at the source yields 1 unit of energy at your house after the line losses are factored in and the
That's electricity.
that's electricity. So, I mean, there are distribution losses with natural gas, the leaks, other things, distribution losses with oil, distribution losses with everything. But with electricity, it's huge. So that's why that's so big compared with just with burning gas, for instance. But if we do the same magic with, so I can treat this carbon the same way I treated the dollars before, and say, okay, if I'm going to burn this at 280% efficiency, and I can only burn the gas at 80% efficiency, what does that do to the numbers? So what that means is that at 280% efficiency, that electricity is 3.04, and that gas, so the electricity goes down because I'm dividing by 2.8. The gas is going to go up because I'm dividing by 0.8. So the gas goes up to 6.63. So the operating costs go up some. And this, I should point out that what this tells you, one of the things this tells you if you track these things over time, is that right now gas is crazy cheap, and electricity in New England is the second most expensive electricity in the country after Hawaii. Wow. So that's a challenge. That's a real challenge these days. But if you're looking at the carbon impact of doing a fuel switch, even from oil, the oil is even worse. It's 7.38. So the fuel switch, from a operating carbon point of view, from oil to electricity is amazing. You save operating money, but you save a huge amount of carbon. Gas for electricity, it still works. All right.
This unit is metric tons of carbon per unit of...
Per 100 million BTUs used to deliver a certain amount of heat. 100 million BTUs is a lot. Average Massachusetts dwelling unit for total energy uses about 109 million BTUs. Average Massachusetts house uses about 6.5 tons of carbon. That's just for that's lighting, space conditioning, ventilation, appliances.
That's a single-family home as opposed to an apartment?
Single family, well no, it's all dwelling units. So there's apartments, single family homes mixed in there. Question here and then there.
Nuclear. When Pilgrim shuts down, how will this change?
Depends on what replaces it.
It's going to be gas, isn't it, in the short run?
Probably.
Yeah.
I mean, we're at 60% gas now. And you just can't burn fossil fuels. Well, anyway, so yes, you got a question.
His question is more interesting.
Well, do you want to ask another one then? Do you see your time?
So it's just a point of clarification with that last number you wrote there, the 7.38. Do we have to apply the conversion factor of 80% to that one as well?
No, I already did.
Oh, okay.
Yeah, that's what I'm doing.
Gotcha.
So, because you can't. I mean, it's pointless just to compare this because you can't.
I thought
you can't
when we went
burn
from
oil.
gas on top to gas on bottom, we applied the conversion factor and then the...
Yeah, you cut them.
Yeah, it's the same
Oh,
Same number.
well, isn't that amazing?
Well, just to make sure we're all on the same page.
I did that.
Because we're following you.
That's why I did that. 7.38.
You multiply by 0.8.
I screwed up a formula.
It's okay.
I will do an asterisk there. When Carrie's speaking, I'll fix it. Yes.
I just wanted to ask, why is electricity so much more expensive than gas in New England?
Why is the electricity so much more expensive than gas
In New England.
in New England?
In particular.
Because so much gas is wasted when you produce electricity with it, in part. In part also because in Massachusetts and New England in general, we're trying to promote renewables. And we've got, it's just undeniable the way rates are structured now. That has bumped up costs to get those renewables online. There's
Cost, but not the, ultimately,
not ultimately, no. There's
cost.
a lot of evidence now that people are able to sell the renewables at cost parity or even better than the fossil fuel sourced electricity. I think. We could get into the grid mix later, but
Okay.
I want to.
Just basic.
But right now, I'm still trying to figure out why I got that. I think. Rest assured, all right. So I'm just gonna. So that's.
It would be about 8.8-ish,
Thank you.
to put that in.
If you could sit up here instead of Mike, because Mike's not helping me out at all. So that's just. Those are numbers. That all had to do with what are the implications of various different fuel sources and different efficiencies to heat and cool your home. It has nothing to do with changing the load of your home, changing how much heating or cooling it needs to be comfortable. That has to do with building enclosure improvements, insulation, and air sealing. You try to find the sweet spot. So this switch reduces the carbon, considerably. Insulation and air sealing is going to reduce the carbon potentially considerably too, and Carrie's going to talk a lot about that. So at some point you need to figure out, you need to be looking at the cost per ton of carbon avoided or reduced. So just put that out there. You need to be thinking about that. You need to be thinking about that when you're evaluating measures on your house, certainly at scale. As policy, as a group trying to influence policy, we have to think about cost per tons of carbon, it is. So just hold that thought for the moment. So the next thing you need to think about is how much carbon. So this is just operating carbon. To reduce the operating carbon, we have to invest some carbon in that building. Yes?
What's operating?
Operating carbon is carbon required to heat and cool a building, to keep the lights on, to run the refrigerator. So it's the carbon that all the energy usage to operate that building represents. So that's what I did here. So I turned all the potential fuel sources in your building, I turned them into carbon. And then, so if you add up, typical Massachusetts house, if you add up the carbon impact, carbon content of the natural gas, the electricity, it's about 6.5 tons of carbon per dwelling unit per year, roughly. So that's what I mean by operating carbon. That's just lighting, cooling, heating, appliances. And we're trying to reduce that because that's year after year after year after year. We incur that cost. But to reduce it requires some carbon. So do you get what sort of carbon I'm talking about? I'm talking about the carbon, a heat pump. Takes carbon to manufacture that heat pump, to deliver it to your house. Takes carbon to get the crew from their homes to your house to install it. The solar panels takes carbon. To insulation has a carbon footprint. So the critical question is, how much carbon can we invest to reduce carbon? We have done projects Deep Energy Retrofits, where it's going to take 75 years to pay back some of that carbon. And do we have 75 years? No. How many? So 6.5 tons of carbon to operate a house. How much carbon are you prepared to invest in year one? And how much do you need that carbon investment to reduce the operating carbon for it to make environmental sense? Now, I don't have an answer for you, but I know you have to come up with an answer, or we have to come up with an answer if we're going to be able to make intelligent choices. So I will tell you, just with regard to drawing our boundary conditions around, and I'm almost done, so don't worry. Drawing our boundary conditions around the building, if we're just looking at the building, I will tell you what I believe I have vested, two things: duration of the project and material choices. You cannot do projects that last months and months and months. Massive deep energy retrofits last months and months and months. You got to be very careful about that. I like to think in terms of short duration, light footprint. So, and in part because there aren't that many people who can do this work, and if those who are doing the work are taking months and months and months on each project, that means there's all those projects that we're waiting. I mean, I would love to get more people trained. We're all working hard on that. Michael is a leader in that regard, getting the jobs opportunities, but that's a slow ramp up. And then material choices. The second dial is material choices. We can't be doing these things with spray foam. Certainly not spray foam with high global warming potential blowing agents, because it's 2 steps forward, 6 steps backwards. It's hard. It's so easy to get good insulation and good air sealing in so many different conditions just by using spray foam. It is a miracle product if properly installed. But we just can't, we've got to figure out how to make the hard ways easier. So for the most part, plant materials that ultimately came from plants. And I'm not talking about oil. I'm talking about cellulose insulation. There's some really interesting wood fiber-based products, like a rigid foam insulation made out of wood fiber, something called Butex. So we have to be thinking very hard about the embodied carbon of our products and the duration of the projects when we're thinking about these retrofit projects. So what are the good measures? What are measures that we know work? Air sealing. Typically air sealing, you can get the low-hanging fruit with a short duration, light footprint project that reduces the carbon considerably, or can. Solar PV, we know that works. There is an embodied carbon there, but it pays for itself in 2 to 5 years, depending on a few factors. What's that?
Solar what?
So photovoltaic panels.
Oh, no.
Fuel switching, we talked about, getting off fossil fuels, moving to electricity is long. Well, and Mike's got some caveats on that, so I won't say any more about that. And then just one last thought. So I was saying I was drawing the boundary conditions around the building when I was talking about those measures. But now let's draw the boundary conditions where they belong, which is global, or at the very least regional. And then what you realize is that if we had a carbon neutral grid, we wouldn't have to do anything on our buildings. They would be, by definition, their operations would be carbon neutral. The manufacturing of the products would be, there would be such a significantly reduced carbon footprint. So we have to figure out where the sweet spot is between cost to decarbonize the grid and cost to lower the carbon of our buildings. And that's, at some point, the cost per ton of carbon avoided at the building far exceeds what it's going to cost to save a ton of carbon at the grid. And so at some point we have to stop looking at our buildings and start looking at what it's going to take to decarbonize the grid and those social costs. You know, I have and think, you know, even as a remodel, you know, it was hard for me as a remodeling contractor because, you know, the old joke about if everything's a nail if all you have is a hammer. I mean, if you're a remodeling contractor, every solution out there has to do with remodeling houses, but it's not true. We have to think beyond that. And at one point I realized that for the price of about 6 whole house deep energy retrofits, I could buy most US senators. And that was probably going to be a much better use of the money. And then so let's think about how we're spending our money, where we stop investing in buildings and start investing in other things. And that starting investing in other things needs to be in people too, because we need a lot more talent out there working on these buildings, and there are too many people who we are not investing in. And then the last thought is that there's a lot of people thinking hard about this and realizing that it is now conceivable that to build a building so that it's a carbon sink, so that it is storing more carbon than is expended in its construction. So we, with a concerted effort and greater awareness, we can turn every new construction project into something that's, I'm not even sure, net carbon positive, net carbon negative. We don't even have the vocabulary for it yet. But even retrofits, even like a deep energy retrofit, could become, with the right materials, plant-based materials. Plants are about 50% carbon. You use enough of it, you replace your sheetrock with plant fiber panels. You replace your rigid foam insulation with Gutex. It's conceivable that we could be turning every retrofit not into just a carbon reduction project, but a carbon sequestering project. And if we're going to do anything like what Boston wants to do, that's the sort of thinking we need to bring to bear. And that's it. Thank you.
Wow.
Paul really set the stage for questioning if what I'm about to show you is actually worthwhile. And what I'll say is I'm a remodeling carpenter. I'm going to remodel houses no matter what. That's what I do. That's my career. I feel guilty about what I do. And it makes me feel better to be able to do the right thing when I'm doing something. So even as little as a kitchen remodel, almost every time I try to make sure it's a gut remodel and we address the air sealing and insulation and all that sort of stuff while we're at it. And that really goes to even re-siding a building. Now, let's really talk about adding insulation on the outside of your building. Now we really have to talk about what that material is, how much of it to put on, and whether that's carbon neutral or positive or negative or however you want to refer to it. So that's where we're coming from. So the question is, how do you define a deep energy retrofit? And I don't know if there's a strict rule of, there certainly isn't a building code that says deep energy retrofit, but the main goal is that we want to do beyond what is called out in the building code, the energy code. And here's just a good example. The DER, Deep Energy Retrofit rule of thumb, originally came from the Building Science Corporation, I believe, which has been introducing these ideas and doing the research to vet out whether these things work and what's better and what's worse. But this is the general idea. And a lot of what a deep energy retrofit is increasing insulation levels by about double what our code is. We want to step up the efficiency of our windows. Generally that means going from double pane windows to triple pane windows. And airtightness is a big one. Airtightness, not very strict in the building code, and the tighter you get it, the less energy you waste through those holes and cracks. So in a deep energy retrofit, we aim to get it as tight as possible. There is one caveat that I put down below, is in a, you can build a code, you can build a house to code and make it really airtight, and the building code allows us to use bathroom ventilating fans to ventilate the house, to get you fresh air to breathe. And as you can imagine, if you try to push air out and none comes in, you're not pushing air out. So ventilation, I have a suspicion that this building code, that even airtightness is still makes contractors crazy. They think all houses are going to rot. Even my recent construction supervisor's license class, the instructor would say, you know, here's what you have to do now for energy code. The jury's still out whether it's, you know, these buildings are going to rot or fall apart or whatever. And it's not true. This has been done for a long time. The science is actually fairly easy. It works. It's all for the best. So get as tight as you can, but we need balanced ventilation. All these, if you're going to make a house airtight, great, make it absolutely airtight, but we do absolutely need full-on, dedicated, ducted ventilation systems. It's just something we don't address in general, and it's a cost. So I'll get into some real nuts and bolts. This is a project I was part of. Actually, a big Meister project that I was hired to do the outside work to. So it's not quite a gut remodel, but it was pretty darn close. And it's a classic deep energy retrofit. So this is before. You couldn't be more complicated in terms of angles and facades. So of course they all start out with strip it off, get down to the sheathing, and that's generally the point where we didn't do it here, too technical, but this is generally the point where I put something on the building that makes it now airtight and testable with a blower door. And you can make repairs, do whatever you gotta do, to make sure you're as tight as possible before you start putting things on. And here it is, underway. It's 2 layers of 2-inch polyiso cyanurate foam board. It's foil faced. In this case, that foam board is actually the air barrier. So it's all taped, joints are all taped. The big gaps are spray foamed in and what have you. But this is, when you say R40 wall, that is 4 inches of foam, 2x4 wall with insulation in it. So that's what you get. In this case, you will see, we actually stripped the roof and the walls at the same time and ran 4 inches of foam on the roof too. So it's one big igloo, like literally like a cooler. Yeah.
Did I hear you say it's oil-based?
Foil based.
Yeah.
Foil faced, I think I said.
Oil-based.
Foil.
Thank you.
So we're worried about, in buildings, thermal efficiency. With thermal efficiency, we're worried about what I call thermal bridging. So materials that are conductive to heat, like the framing in your walls, are just like a radiator on your car or what have you. If you don't drive around your car, they're cooling fins in the winter. So you get a lot of advantage by having continuous insulation over your structure. As part of that, we like to try, if you have roof overhangs or something, you don't really want the wood that's in the interior of the house to stick out through your insulation and be on the outside of the house, you've missed something. It's something that lets heat flow out. So in this case, we wrap everything, and now we added overhangs, which are good for durability more than anything. It's partly look, but durability, keep water off your walls. So everything gets, stripped. 2x4s. 2x4s are what the final plywood is going to be attached to. So this is, we screw through the foam into the main structure of the, and we're sandwiching the foam. Here's added eaves, pretty complicated. This is the corner between the wall and the roof. So these scrapping pieces hang along, and this assembly is hung from it. Soft assembly is hung from it. And when all is said and done, you wrap all that ugly stuff, and it looks quite nice, and you wouldn't know it. One thing, there's just a little. It's actually hard to see here. Because it's a thick wall, when you put windows in, sometimes you'll notice that the wall is thicker either from the inside or the outside. And I will say that these are not only triple glazed windows, but they come from Europe, as all good windows do. And these are what we call an R value of like 7 compared to 2-ish of what would be code. So turn windows. And of course, again, just blower door. If you haven't seen it, blower door to address air tightness. On the side, I have a project. This is actually a 1780s cape that with comfort issues. And so between moisture management and insulation and being able to maintain a 1780s house, it was an interesting project. And heat recovery ventilation. So all airtight houses need heat recovery ventilation. And this is a unit that takes air from outside and air from inside, and they cross streams. And energy-wise, fresh air comes in and is heated by the air that goes out. And so there are no ducts been shown in this picture yet, but there'll be a pile of tubes coming out of here that go to every room, all over the place. So that was an all-in-one house. Basement got insulated with spray foam, and everything else was really exterior.
And what did that run?
Cost? I don't totally know, but I'll tell you that it was, so I'll say the extra cost of adding insulation around the outside and holding that insulation in place to put new finishes on, 200,000 more maybe? Yeah, big house, but it is what it is.
And does that include adding that new balanced ventilation?
Probably not.
And how much might that have been?
10 to 15,000.
I'm not sure if this is a relevant question, but in terms of that outdoor insulation, is there any bearing on indoor air pollution in relationship to that?
To the product itself?
Just even the process, what you're doing, because you're talking about completely airtight, right? I'm just aware that indoor air pollution is a big issue. So do you look at that relationship between what?
Absolutely. Certainly Mike is more involved in actually monitoring how effective this is, but we are designing the ventilation system to accommodate exactly what you're saying. It's supposed to remove the pollutants. Now, you can argue that a not tight house, a very leaky house, is far more, could be far more polluted because Air could be coming in through your basement and it's all moldy and whatever, and then exiting through your roof, or the opposite in the summer or whatever. I mean, when air is moving around throughout your odd spaces and walls and yucky stuff where mice live, it's not a good thing. So it's something to be concerned about.
Did that house get electrified? Totally, so there was no gas or oil being used in that house?
I believe that's true. Maybe cooktop? Maybe? No, not even? Yeah, so nothing. And they have an adjacent garage with like a 10 kW array. The whole point was it's supposed to be net zero capable. And the math said it would be. I don't know if the jury's out, but it was not that long ago.
Is it correct to say that air tightening is a large category, and insulating is under that, it is part of that, and then filling in tiny holes is the other part of that?
In terms of order of most effectiveness for saving energy,
Yeah, there you go.
I think that's fair.
Okay.
I'd like to hear from these guys about that, but I think that's fair. And especially in light of the idea of what material are you using for insulation, what's the carbon footprint of that material, and I guess there's the order and my obnoxious truck that goes back and forth. So yeah, so you don't have to do all this work as one big project.
Yeah.
And this is where most of my work is almost never this. It's always a piece of the puzzle. So, Cape style house, second floor. This was actually a renovation of a renovation. The first contractor did a horrible job. And lots of ice damming and leaks and all that sort of stuff. So, very shallow old houses have 5-inch, 5.5-inch roof rafters. You only get this space, but you want this much insulation. So in this case, spray foam was the choice because of that. We're limited on space. It's the highest R value per inch. It was a low global warming potential spray foam. And I wasn't using it for a while until this product came out a few years ago. And now it's pretty much what people use. It's on par global warming potential with other insulations. So make the rafters a little thicker with some foam board separating the rafter from a new strapping surface for sheetrock. And actually it's too dark, but here's it before and here's it after. So we fill it right up, full. And this woman tracks her energy. She doesn't turn the heat on upstairs anymore. Totally comfortable. Doesn't regret a moment of it. Mm-hmm. Strip the ceiling, insulate it, put the ceiling with all the stuff back. That project also is this one. There is a little area of that was not accessible from the inside, so we spray foam it from the outside. Put it back in. Again, I think this, if I remember correctly, this is about $40,000, all said and done. And we didn't really change the living space really in any way. We prevented ice damming, and we prevented her using excess heat.
It's cheaper to get it right the first time.
Yes.
And it was, there were structural repairs, all kinds of stuff. So.
Do you have a sense of if she'll make that money back in terms of energy
My answer
savings?
would I think exclusively will always be never. There's no return on investment. No, you're doing it for a different reason, and often these reasons are durability, to be honest. Again, we're fixing. We've got a byproduct that the house is more comfortable and more energy efficient, but the ultimate beginning problem is that heat loss causes leaks with snow.
Also secures a good price though, Tom.
Pardon me?
Her price, so a sale price is probably improved by
Yeah,
having done
Good
that.
point, yeah.
Yeah, it's hard to quantify comfort. And I can't say enough between the triple glazed windows that we're pushing, you do the math's not very good. You pay what you pay extra versus the energy you save. That's not that good. There's not a return on investment there, I don't think. The comfort, on the other hand, is night and day. So this is one thing that she really talks about, is how much of a different place it is to live. Basements, do a lot of basements. Again, basements tend to be wet areas, at least damp, humid. Another place, as of this point, I don't know anything besides a foam product to use that is effective in a basement. Anything else can be mold prone and moisture prone. So this is impermeable to moisture, and we do usually about 3 inches of this foam is about R20.
It's a closed cell, right?
This is closed cell. I only use closed cell.
Right.
If you know anything about foam, no open cell anymore.
You said closed cell?
Closed cell.
Close the opening.
This is a high density foam. It's closed cell. In other words, it has little bubbles in it. The thing, the HFC, HFO, the global warming potential comes from this blowing agent that turns this liquid into bubbles. And with closed cell foam, they're very dense and the bubbles are closed. In a open cell foam, it's fun videos to watch. It expands like 100 times its liquid size, but the cells are open and it allows vapor to go through it. And it has lots of installation issues, lots of voids and stuff like that I've never seen go away. And it allows moisture through, which probably too technical, but it could allow your roof wood to rot. It could in itself. So you do it all in one, product here. While we've got so this is, especially in older basements, we have a lot of stone around here, rubble basements and stuff like that. Spray foam is the only choice, and it makes the place completely different from a musty old basement into this project right here. Actually, this guy said the entry above averaged 5 degrees warmer in the winter. Just from that, the basement is so cold. So he's thrilled, and he added a little value to his house.
You typically remove concrete basements and insulate underneath them, the floors?
No.
You just leave the floors alone?
Stay tuned one moment, because right there. So, a few years ago, National Grid was sponsoring Deep Energy Retrofit pilot program, and they were giving money out for Deep Energy Retrofits. If you've got a good project that needed siding, especially siding, windows, whatever. I think my first one with Big Meister was a small ranch in Framingham. It still was its vintage 1945 look with aluminum windows that rattled and aluminum siding and all that sort of stuff. And a new homeowner bought the place, was waiting, and needed all this stuff. So he got $30,000 actually from NSTAR to implement the extra cost of triple pane windows and insulating the basement, insulating the attic, and doing all the walls. It cost more than that, but but there was a program that was doing this. In this case, this guy got funding towards doing a basement deep energy retrofit. So what that involved, as part of the program, you got money per square foot of what you addressed. So he got money incentives to insulate the floor. This is just a regular concrete slab. Put a dimple mat that has a little air space on top of the concrete. Then you put, in this case, EPS foam, the white stuff like styrofoam cups. low global warming potential product that is very waterproof. And in fact, that's exactly what this stuff is on the floor. The 2x8 sheets are, it's R10. Would I do this in a, without the incentives? Generally people aren't, because it's not saving energy so much as reducing the likelihood of condensation on your slab. It's a cold spot that's always 55 degrees if it's uninsulated. So the heat loss through it is not really that big. So you weigh the cost versus the cost benefit.
Well, what about the increase, but you said a minute ago that at the level above, it was a lot warmer after you did this? Was it this particular procedure?
It was not this particular one, but it's the same thing.
So.
And this is exactly. This is just what I should say, this is a method not using spray foam to achieve the same result.
Yeah. But there is an energy saving in that it's warmer somehow.
Absolutely.
Yeah, so I guess I misunderstood.
Yes. Plus, I believe he used an electric heater once in a while. He had an office in the basement. He did his best, but had to use a little electric heater, something here and there. So what I was saying is, yes, there is another way to do this without spray foam. This is sheet foam. Again, it's polyiso cyanurate foil-based foam, where you can take the joints and make it airtight. We additionally make it airtight to the wood, which then caulk all the seams and everything like this. So everything from the ceiling of your basement down is airtight all the way across. And again, foam, plywood goes, it's hummingbird plywood, go right onto the foam, screw it in with concrete screws, and you can put whatever finish you want on the floor. And in addition to the foam board we put in, we built another wall-in board to put sheetrock on, and fill that with another vat of rock wool, and as well as filled the upper part with 2 layers of that. So that's actually R40 in just a fibrous product, and roughly that below too. That gets a vapor control layer on it that is not shown. Yeah, I guess that's it.
This is where we live, and fun fact, let's say we took the world and shrunk it down to my size. It's 6 feet in diameter, all right? Let's say most of the atmosphere is below Mount Everest, 29,000 feet. Let's say we shrunk it down, so we have a 6-foot diameter sphere. How tall would Mount Everest be, below which most of the atmosphere is? Somebody guess.
Millimeter.
Small. Wow. About 51 thousandths of an inch.
Wow.
So this layer that we depend on for life, and into which we're releasing a lot of CO2, is really, really thin. 1 gallon of gasoline, 6.3 pounds, releases 19 pounds of CO2. How is that possible, right? Because gasoline is a hydrocarbon. Hydrogen combines with oxygen and makes water. And carbon combines with oxygen and makes CO2. Fuel oil is worse. Gas, similarly. So Paul talked about this, and I just want to quickly point out what we're doing here. So the block we're going to focus on is electricity generation. On the left here we have all these inputs. We have a little bit of solar, a little bit of nuclear, hydro, wood, geothermal, wind, and natural gas and coal. Those are the big inputs to the electricity block. What comes out of the electricity block is we've got 37 quadrillion BTUs going into this. This is an energy diagram for the entire United States. And how we make electricity, we put in 37 quadrillion BTUs, it's a really big number of energy coming in, primary energy. And we have 12 or so quadrillion BTUs coming out as useful electricity, the rest is waste heat. So that's the big thing that Paul was talking about, generation. That's why electricity is so dirty, right? Because we only get, if we put in natural gas and coal, we only get out about a third. So the primary energy factor is about 3. It's about 3 to 1, just roughly. So Massachusetts has this Global Warming Solutions Act, right? And they're moving to do a reduction of 80% of CO2 by 2050. The way they're going to do that is they're going to generate a lot of electricity renewably. And one method is they're going to get a transmission path through Maine and bring down Hydro-Quebec electricity, which is low CO2. And another thing they're going to do is put wind turbines out in the ocean, right? And so this process needs to get started and move along pretty quickly. And then finally, we're going to electrify all 3 million buildings in the state, except for the ones, as Terry pointed out, there it's going to be too hard to do. So 3 million buildings, we're going to do this in 30 years, it's 100,000 buildings a year. We're going to improve the energy efficiency of them somehow. We're going to electrify them so they don't use fossil fuels. That's the plan for the Global Warming Solutions Act Implementation Advisory Committee Building Subworking Group. Everybody wants to see that recommendation, I can show you. So, the world's largest offshore wind farm is in the Irish Sea. It's an enormous facility, right? So they're doing things over there. This is 5 6-megawatt wind turbines. This is off Block Island, okay, out in the ocean. That is the entire installed capacity of offshore wind in the United States today. We got some catching up to do. So you've heard about the procurements of offshore wind. You've heard about the leases. These are the leaseholds out in the ocean. Here's the little Block Island wind farm. So there are big plans out there, but they're not here today. This is going to take some time to build out and some expense and all that. But the first procurement of, I think, 800 megawatts came in at a surprisingly low price. People with DOE, our Department of Energy Resources, were shocked at how low of a price. So they're trying to get together with other states and aggregate this. So electrification and displacement of space heating is a big part of the plan that they have. Whether or not we'll be able to implement it remains to be seen. So Paul was also talking about this idea of operational and embodied energy. Just to give you a little bit of a picture of this. So the embodied energy is in green, right? And the embodied energy, let's say this is a deep energy retrofit. We're building a new house, your pick. You start out at the beginning and you do the work, right? So you add all this embodied energy with insulation and heat pumps and all these other things, and it's there, and it doesn't change. And then you have the operational energy, right? So you start using electricity, natural gas, or whatever, hopefully all electricity, and year after year, your total electricity operational energy, CO2, goes up. So this is good and bad. The good thing is the embodied energy doesn't go up. The bad thing is you spend it all now, right? It hits the atmosphere right away. So we need to be very careful with releasing large amounts of CO2 into the atmosphere by doing things that create a large amount of embodied energy. Paul talked about the ability to build houses and actually make them a carbon sink. Now do you see why that's important? Yeah. Okay, great. All right, so let's take just a 1978 built house in Stowe, typical Stowe, Mass. Happens to be my house before I started working on it. And if we break down using a computer model where the energy goes, and we have to say, we need to reduce energy use dramatically, which slice of the pie would you choose? All right, so we're there. That's why so much is focused on heating. So
Can you just tell us what you had installed for heating and cooling for like sources?
This is strictly building load, so it doesn't really matter.
Okay.
In other words, this is the heat I need to put in the building, the heat I need to take out to form cooling, how much energy I need to make the hot water, and then lights and appliances. So independent of the mechanicals, really. It's looking at the load you have to serve, which is kind of what deep energy retrofits are about when you think about it. I'll flesh this out a little bit more. So let's just focus in on that heat loss slice of the pie, okay? I've got a computer model now that shows where that heat is lost. So it gets lost in things like the ceiling, 14%, and the rivet band joists, and the walls, and the foundation, and the doors, and the windows. Infiltration. Wow, look at all this. This is air coming in and out of the building, taking heat out. And it takes so little material investment when you make a building new to do air sealing, right? You need a little bit of fabric or a little bit of tape. You don't need to use caulk if you plan a building out new. You can use tape, nice Euro tapes that are acrylics. So air infiltration is a huge lever, but the problem is when you have an already built house, it's underneath the siding, and you'd like to air seal it. That's another problem with deep energy retrofits, which if you take the siding off, it's a big advantage. You can get you that airtight air easily. So I look at a house from a space heating perspective like a leaky bucket. We've got a lot of leaky buckets around, and we're pouring in heat. So we have heat leaking out, and we have a heating system adding heat in. Now you start to think, gee, wouldn't it be a smart idea to plug these leaks? So wouldn't it be nice to do that? And this is the thing that passive house technology does a lot of things. But the big thing it does is it crushes space heat demand. It makes it minuscule. And then the heating system to add heat becomes very, very trivial. So there's a savings there. And if you do a deep energy retrofit, you have the same sort of thing going on, perhaps not to that extreme, but that's the concept anyway. So, Terry was talking about a house in Framingham. This happens to be it. This is the floor picture, right? So it's a 4-bedroom ranch. I think this used to be a garage, right? And they turned it into another bedroom. And this is the after picture. Terry's wrapped this thing with 4 inches of foam and then air sealing, and there are a bunch of air source heat pumps heating it. And we've got a nice PV array, what, 10 kilowatts? Is that about right? So is this net zero, or it's probably pretty close?
It should be. They don't live particularly frugally on energy.
Yeah. So anyway, there's that. And so now let's look at some data, right? This is site energy. This isn't primary energy. This is the electric meter at the building. And you can see here in red, we have an estimate of the amount of electricity we would have used if it was just heat pumps and we hadn't done the container, we hadn't plugged the leaks in the bucket. And after is actual real data. So you can see there's a dramatic difference in site energy, right? We've really crushed space heat demand. But here's primary energy. This is the other part of the story, right? Now this is the amount of CO2 that's going into the electricity generation block, and we're losing 2/3 of it as heat. So
Could you just say that again?
yeah. So site energy is the electric meter on your house. But if you step back to before the electricity generating plant, remember we've got 3 units of electricity of fossil fuels going in and 1/3 coming out and getting to your house. That's what this is showing. So there's an impact there. And yes, we've made it a big improvement, but the improvement isn't as big as you think unless you make low carbon electricity. The plans for Hydro-Quebec and the plans for the wind turbines out in the ocean. So things have to happen all together. All the pieces have to come together for this plan to work. And there are a lot of moving parts. So again in red, pre-project estimate for heating, and blue is the actual data we've taken from the, so we've crushed space heat demand, right? That's one thing deep energy retrofits do well. They didn't have air conditioning before, but air source heat pumps do that, so they do now. Domestic hot water, a more efficient electric system, and lights and appliances. So the total is a great decrease again in site energy. And in primary energy, not so much, again, because we're counting all the fossil fuels generated to make our current electricity grid work. Pre-project estimate. And notice that it goes down after a couple of years. This was learning, right? This is one of the first projects we did with air source heat pumps, and we were learning. And a really good system was actually installed, but they were trying to use it like a fossil fuel-based system and setting it back at night, lowering the temperature, and air source heat pumps don't like that. When you have air source heat pumps, you set them up, you run at one comfortable temperature all the time, you leave them alone. So they learned that, and that's the energy reduction business. Not only did they use less energy, they were more comfortable. So new technologies, new things to learn, and in this case, it makes you more comfortable also. A win-win-win.
Mike,
yes.
Just one furthermore, turning the breakers off. They start
That's another thing. We've learned things by detailed energy monitoring. When you don't need these things, if you turn them off, they use less energy. Because they use a little bit of energy, but they're not doing anything for you in the way of heating and cooling. Yeah. But there's a way around that with thermostat, but there are lots of details. Of course thing. Okay, so here's another project. This is another big Meister project. And this is in Belmont. Here's the before picture. There was two families that had homes that were not very good, and they bought this home, which really needed help. It needed new siding, it needed new windows, it needed new everything. So all that stuff was coming off. It was a great opportunity to get at it underneath, make a good air barrier, add the foam, and then put the siding on. So a great candidate for like a deep energy retrofit. Very simple shape, right? Nothing crazy like that first house that all the ins and outs. Just a very simple box type thing. And so that one worked very well. The blower door was a very big thing for us. Like we didn't have much experience tightening houses to a very, very airtight level. So before it was 5,700 cubic feet per minute at 50 pascals of test pressure. And the pilot program goal was 750. And Paul negotiated with the client for a pretty low number. And his crew beat it. So this is, right, a factor of almost 10 reduction in air infiltration. Remember that big slice of the pie, the air infiltration part? Mm-hmm. Yeah. So that was a very important part of reducing energy, space heating energy demand in this house.
Can you describe exactly how that blower door functions or what?
So you open a door to outside, you put the blower door in, and it blows air out of the house. Blows it out, and you adjust it. So the pressure across inside to outside is 50 pascals. A tiny amount of pressure, like a 20 or 30 mile an hour wind blowing on the side of the house. Okay. So then air is leaking in, and all the air that leaks in goes through the blower door fan. And the blower door fan has a measurement device. It measures how many cubic feet per minute of air is going through it. So the test pressure is like the force that you're exerting, and the blower door fan measures the volume of air. Does that make sense?
Yeah, but so the actual function is to keep exterior air from blowing
So the
into
actual function is simply to test the leakiness of the building.
Oh.
And the reason is this. Well, no, it's a good question. It's a good question. So the reason is this, right? The leakiness of the building, there's no blower door fan in there normally, right?
No.
It's not. So it's to measure the leakiness of the building, because when the fan is gone, what happens is stack effect. It's colder outside than it is inside. Air leaks into the basement, warms up, and then it comes into the house and absorbs some more heat, and it leaks out the ceiling. And so what happens is air washes through the building, comes in and goes out, and that cycle is called convection. And that is 25-30% of your heating bill. And it takes all the moisture out of your house and makes it very dry in the winter.
So you take that blower door out after you've done your
That's
assessment.
all done. And what it's done is it's measured how leaky.
Yeah.
It measures how leaky your house is. So no, it's a really good question. You have to make that connection.
It tells you where the leaks are too.
Right.
It tells you where the leaks are.
Yeah, so there's even more. And there's more, right? So if it's cold outside, it's warm inside, I put that fan in there and I run it for about 10 minutes. I can use an infrared camera and I can see an air leak across the room because the cool air washes over a surface, depressing the temperature even a couple of degrees. You can see that clear as day with the infrared camera. So you can find air leaks. And we use this method to drive down that air infiltration method. Because as you find leaks, you fix them, you watch the blower door number go down, and then when you can't find any more, you say, well, that's good enough. So we can do extremely airtight buildings. And by the way, this improves indoor air quality, because it means you don't have air going into your building, getting mold spores, chemicals and all that, and bringing you up. Airtight buildings have higher indoor air quality if they have a properly designed and implemented ventilation system, balanced ventilation system. Including if you're susceptible to allergies and things like that. If your building is airtight, you have one place you're bringing air into your heat ventilation system, your filter is there. Pollen stops coming in. And if you're concerned about particulate matter, PM 2.5 from diesel trucks and things like that, you put a better filter in there. And your air is much cleaner than outside. Airtight building, yes.
When you're assessing higher density buildings with multiple units,
Can you use the same technology, or do you have to take it unit by unit?
Absolutely, in fact, it's easier with big buildings. Yeah. Because you can take a more organized approach, right? The bigger building has more units to treat, so there's a bigger budget for engineering, for design. We just completed the first multifamily passive house certified in New Hampshire. It's low-income housing. Didn't spend a lot of money. In fact, they got a very small amount of money because it was passive house certified. But now each unit has ventilation, specifically balanced ventilation. It has nice thick wall systems. It has really high performance windows like Terry was talking about. Low income housing. This is all over Europe. This is what they call social housing.
That can co-product with reductions in asthma and other things.
Correct, exactly. Yep. In Europe, they've got this down. They're social housing, they own it. They know the operating costs, they want people to be happy. I've gone into a basement and seen 15 or 16 heat recovery ventilators. Each unit has their own.
Wow.
Okay, so Belmont site energy and primary energy. Again, not too much of a difference here. The reason is that Belmont hung on to natural gas, and that reduced their primary energy to site energy. And then pre-project estimate. You can see we crushed space heat demand, did a really good job there. We didn't learn anything because there was a natural gas furnace and there was nothing to change here. So, 1,000 home challenge from Hello. This is in Jamaica Plain, another deep energy retrofit. Where's work on that? This is a big nice project. And annual primary energy, doing pretty well, reduction there. And actual and projected energy use, so a good reduction there also. This is a deep energy retrofit that was done in Melrose, and it has, I think, a 9 kilowatt PV array, and it's been net positive energy since it was done like 4 or 5 years ago. Not a lot, it's like 300 or 400 kilowatt hours a year plus, but everything in the house is run from electricity, heat pump for heating, heat pump on water heater, lights and appliances, induction cooktop, no gas, no fossil fuels. Over $300,000, I think.
Yeah, right.
I don't understand. But if the grid is in green, so how can they not?
It's got to get there.
No, I know, but right now
They're making electricity
with
with
the
their
solar
PV
panels.
array, yeah. So net metering works like this. Let's say it's daytime. Let's say sun is shining on this array. It's making more electricity than you need. It runs the electric meter backwards. You build up credits. Sun goes down, right? Now you pull credits back. In the summertime, you produce more than you consume because you're not heating. In the wintertime, you need more than you produce. But if you have net metering over a 12-month period, it's like a lossless balance. It's like a credit account for your electric.
We have solar panels.
Yeah. So that's how net zero is made much more practical. So that really is it.
Why and how did Europe get ahead? Why are they ahead? You know,
They've been doing this for,
Why?
So
Political will.
Humboldt was a German scientist.
Yeah.
He first heard about climate change in the year 1800. The Germans have been on this for a long time. Dr. Feist created the Passive House standard specifically to address climate change 30 years ago. This has been well known. They get it.
Well, how can we transpose that will?
There's a good question. I don't have the answer to that.
That's the ordinance.
That's what we're here for.
Our new campaign is focused around the largest buildings here, the worst offenders, and I watched that video that you recommended and you had some of the slides from there. There are some magic materials to have carbon sinks in new buildings like this hempcrete.
Right.
Yeah.
Do you have a magic bullet for insulation instead of using foam? Use something that absorbs carbon for old buildings, for retrofits. Blown in cellulose?
Yeah.
Because I think that's kind of the direction that we would have to go and push.
So Northeast Sustainable Energy Association, Building Energy 19 conference happened in March, and there was a video about this.
Yeah.
Is that the video you saw?
Yeah, exactly. They
Yeah.
send it around. We should watch
Yes,
it before the
that's
presentation.
a great one to watch about this concept.
And yeah, so that you use materials that actually
Right.
bind
Six
carbon
percent
rather than using the blow foam that will, as you showed in your diagram. If you insulate the house, first you increase the carbon footprint and then you decrease it. And so I think we can't afford this anymore, basically. So we have to look at materials and propose that the city puts regulations in place to use such materials. I guess that's probably our angle. We need you for that.
Asking that,
Yeah. Oh,
while
so
a building is going
why don't you
through a
put
deep
that
energy retrofit, can people live there? Can it be used, functioning, whatever it is the building is? Mostly housing units.
Karen, why don't you take that?
It's hard. I did a study tour of with NESI, Northeast Sustainable Energy Association. A small group of us did a study tour of a couple study tours, and we visited a major apartment retrofit near Stockholm, where it was more cost effective for them to give all the occupants a 5-week vacation to Turkey to get them out of the building, so that they could retrofit while they were all gone. It's hard. I mean, you have to insulate from the outside, and a lot of building types lend themselves to that. You know, ugly buildings from the 70s that are made of masonry are great candidates for exterior insulation. Because it's only an improvement. And if tastes change, we can, when we solve the climate problems, we can take that insulation off, and the building will be perfectly preserved underneath. But then you still have to get into the apartments to typically to add some sort of central ventilation system, some distributed ventilation system. I mean, so it's and in the 3 family that Mike showed, the two it was owner occupied, 2 units were rented, and it was like dealing with 3 different clients with 3 different very different sets of needs, and it was tough. To me, that sort of situation lends itself to the short duration, light footprint approach, where maybe you super insulate the roof, put some PV on it, and then you figure out how to do a fuel switch.
So if the city wants to retrofit a lot of these larger buildings and there's issues with like building functionality while that's happening, like what do you think is the approach to doing retrofits on large buildings like that are commercial spaces?
Every building needs systems upgrades, finishes upgrades. So at some point in its life, every building needs a pretty significant overhaul. Sometimes holistic overhaul, sometimes piece by piece overhaul. I would just make really sure that you get it right at those moments. And too often we are not getting it right when we do the upgrades. We're not when the space has been gutted. We're not testing with a blower door prior to putting the wall finish back up. So we're locking in flaws in the thermal enclosure for another 40 or 50 years to the next upgrade. So we don't have plans we don't have master plans for most buildings. Most of our homes, if for some reason boilers have a propensity to fail on the night before a major holiday. So the equipment's replaced. So the equipment's replaced with whatever the technician has on the truck. So you're locked in for another 25 years. So put a plan together and implement the plan over time. We also, this structural issue is, I think, the mortgage interest deduction, which encourages people to buy houses that are bigger than they need to be. So the costs of maintenance are disproportionately high with regard to household resources, and so the maintenance doesn't get done. I mean, more often than not, when someone asks us to come in to consider a major renovation project, a good half of what we're asked to do is catch up on 20, 30, 40 years of deferred maintenance. And so we're just not budgeting properly to fix the systems. I don't have I don't have a magic wand for you, but there's a systems approach that we've got to figure out. Master plans, incentives, training, awareness.
So what I'd say is one of the things that Paul did back 6 or 7 years ago in Austin, Texas, Affordable Comfort Conference, a full day on stage Deep Energy Retrofits, which was in effect creating this plan, right? As surfaces needed maintenance or equipment needed to be replaced, what could be done, and a plan for stitching the pieces together over time.
That's right. Yeah.
So you're suggesting at a city level that be done?
And at a per building level, really, because the buildings are so different.
How do you implement some? I mean, it's really implementing an awareness,
Yeah.
and I think probably implementing that awareness it does require getting people to be conversant in carbon numbers.